It perfect. I'm recording. We can always edit it a little bit later. Yeah.
Okay. Um, Welcome, learners. Today we'll be talking about theoretical physics. I'm with Prof. Francesco from UKZN. I will start by introducing myself, and then Prof also will introduce himself. My name is Aluwani Guga. I'm a science teacher. I'm a science educator. Currently, I'm doing my master's at the Nelson Mandela in physics, which is a program under nanoscience, which is in partnership with the University of the Western Cape, University of Free State, and the University of Johannesburg. Over to you, Prof.
Good morning. Good morning, Aluwani, and good morning to good day, depending when
Yes.
people will listen to this. Yeah. My name is Francesco Petruccione. I'm the interim director of NITEP. You see the logo behind me. NITEP is the National Institute for Theoretical Physics, but I'm also a professor of theoretical physics at UKZN. And in particular, I'm a South African research chair for quantum information processing and communication, of course, at UKZN.
Okay. Thanks a lot, Prof, for that. So now we'll shoot to questions about physics and theoretical physics in particular. Okay, my first question, can you please explain to our learners, our scholars, what is physics?
What is?
Yes,
Nice.
what is physics?
Nice question. I mean, physics is one of the disciplines of science, and of course, it's the most important discipline in science. Yeah. And I might sound a little bit like Sheldon in the Big Bang Theory. Yeah, and that observes nature and the environment that surrounds this and the phenomena that occur in nature and tries to explain them. Yeah, and the language in which physics tries to explain natural phenomena. Yeah, for instance, like how apples fall from a tree and how planets revolve around the sun and things like that is in the language of mathematics. Yeah, and the reason why we love to do that, yeah, is because the moment you have a mathematical description, you can start making predictions. Yeah, and the moment you do predictions, you can test whether your model works or not. Yeah, because for instance, your model could say that that the sun will come up only at lunchtime. Yeah, and then you look out of the window and it comes up at 6 o'clock in the morning. Yeah, then there is something wrong in your model. Yeah, then you have to go back to to your paper and pencil and come up with a better model. Yeah, so that's essentially what physics does, and in particular theoretical physics. Yeah, so theoretical physics is concerned about formulating models that describe what we observe. Yeah, and and probably your next question would be, what is experimental physics? Yeah, and experimental physics is essentially the observational part. Yeah, so experimental physicists set up experiments to test the models and the predictions that theoretical physicists come up with. Yeah, and of course, you know, the difference between theory and experiment can be a little bit fluid. Yeah, because there might be experimental physicists that also do theory, and there might be theoretical physicists that also do experiments. Yeah, but roughly that is the the distinction. Yeah.
Okay. I get the difference. So basically, you're trying to say that experimental physics is it a hands-on experiment?
Yes.
It's a hands-on type of learning.
Yes, because you want to, you know, you observe nature, yeah, and then you see something, yeah, and then you see, okay, but then I need to understand it better, yeah, and the first step towards understanding better is to measure, yeah, so you want to measure precisely, yeah, so that you know exactly what's going on, yeah, and and only when you have lots of data, yeah, you can test the predictions of the theory with the experiment. Yeah? And of course, the work of the experiment and the theory goes hand in hand. Yeah, because
Yes.
if the experiment shows that the theory is wrong, the theorist has to go back to his office or at home in times of COVID, yeah, and come up with a better model, yeah. And then he sends the model to the experimental physicist, and he or she goes back to the lab, measurement, and comes up, oh, this works better or this works worse. Yeah.
Okay. Thanks for that, Prof. Interesting. Okay. Now let's go to our next question. So, how big or small is this field of theoretical physics?
Theoretical physics is very big. Yeah. Many things start in theoretical physics and then evolve in other theories. Yeah. A very nice example is, for instance, the theory of electricity and magnetism. Yeah. More than 100 years ago, Maxwell came up with a theory that describes all electric and magnetic phenomena. Yeah, and he became famous for the Maxwell equations. Yeah,
that's
and now that's the theory part. Yeah, and now you can study electrical engineering. Yeah. And those guys simply, in a simplified way, what they do is they apply the theory of Maxwell to design devices that use those laws to do things. Yeah, and then once they had the Maxwell equation, people came up with all our electricity grid. Yeah, those are the laws that determine how, for instance, in the South African contest, Eskom produces electricity and how it gets distributed and how it gets converted into work. Yeah, so that we can do things. Yeah, we can switch on the light in our homes. Yeah.
Yeah. So basically, it all starts from theoretical physics.
Yeah, at the beginning, it's also experimental physics because people try to verify the predictions of Maxwell equations. Yeah, but then at some stage it becomes technology. Yeah, and then it becomes engineering. Yeah, and then it gets a life of its own that is probably then might be then maybe boring to the theoretical physicists because they understand the equations. Yeah? And they don't really interested in building stuff. Yeah, but I'm talking a little bit in a rough picture. Yeah, of course the situation is more defined and refined. Yeah, and there is overlap between everything. Yeah, but that's roughly the idea. Yeah.
Okay. Now, can you tell our learners what is it that is special about theoretical physics? Why theoretical physics?
Yeah, theoretical physics. If you ask me, and I apologize if I sound a little bit like Sheldon in the Big Bang Theory. Yeah, it's very important because it is probably the most difficult discipline that young people can decide to study. Yeah, because there is physics, there is mathematics, there is computer programming. There is experimental skills. Yeah, there is data analysis. Yeah, there are lots of skills that you learn as a theoretical physicist. Yeah, and some of those mathematical theories can become quite complex and require a really refined knowledge of the underlying mathematics, and then you need to be able to apply it to solve problems. Yeah? So it's probably a difficult, a challenging, if you have to choose a subject, that's probably one of the most challenging ones. Yeah, but the rewards will be huge. Yeah, because once you have those skills, yeah, those mathematical skills, those computational skills, those theoretical skills, the skills to be able to look at a complex situation and come up maybe with simple rules to describe it, yeah, make you very precious, yeah, because then you're a person that that has really very good problem-solving skills, yeah, and in particular these days where everybody speaks about the fourth industrial revolution, yeah, all the skills that physicists and in particular theoretical physicists learn are exactly the skills that you need to succeed in the fourth industrial revolution. Yeah. So it's you know, it might be challenging at the beginning if you maybe access university and don't have really solid mathematical foundation, but then you can get it there. Yeah. But afterwards, you will definitely be rewarded, yeah, because there will be many different industries and governmental positions and businesses that that might be looking for the skills that you have, yeah. And you know, and the very crucial aspect of theoretical physics is that because of the hard training and the variety in the training, yeah, mathematics, programming skill, computational skill, and so on and so forth, yeah, you have the tools to learn new things very quickly, yeah. You know, some theoretical physicists end up working in financial institutions, yeah, and and do the data analysis, the risk management models, and things like that. And those maybe are things that they don't learn while they study physics, yeah? But they learn all the tools, yeah? They learn about the Monte Carlo simulations, they learn about the differential equation, they learn about the stochastic processes, yeah? And those are all tools that you can apply here. You can, you can apply it to the bank, you can apply them to the insurance companies, you can apply them even for government, yeah, that wants to analyze big data sets, and so on and so forth. Yeah, so it's quite a flexible training that you get that allows you in a very short time to become an expert in almost any field. Yeah.
Yeah. Okay. Interesting, Prof. Thank you for that. So now think of a learner, you know, learners, scholars in the classroom or when they are at home.
Yes.
You know, working from home to school. What are the day-to-day applications of this theoretical physics? You know, examples.
Day-to-day application. I mean,
yes.
You know, you are sitting in front of a computer, yeah.
Yes.
Your laptop or your desktop, I don't know. I can only see you. I don't see your computer.
Yeah.
Has inside chips, yeah, that do all the number crunching, yeah. And those chips are made up of millions and millions of transistors, yeah. And transistors, the concept of transistor is something that theoretical physicists came up with a theory of that. Then, of course, other people built them, yeah. But the theory of semiconducting materials, yeah, is something that theoretical physicists came up with, yeah. So you use it every day, yeah. Or you know, every time you go to the supermarket, yeah, and you see the scanner with the red laser that scans the barcode on on your milk bottle. Yeah. The theoretical prediction of the laser, yeah, essentially goes back to Einstein 100 years ago. Yeah. It took another 50 years until someone built it.
That's true. That's true.
Yeah, but the basic principle came up through the work of the vision and the playing around with crazy ideas of theoretical physicists. Yeah, and you know, probably the example of the laser is a very nice one, because it explains to you that, you know, from the basic principle, yeah, that that Einstein sort of saw, yeah, to building one, yeah, it takes probably 40-50 years, yeah. And those are sometimes the time scales that you need to keep in mind, yeah, from understanding a basic principle And when you understand it, maybe you don't see, you know, Einstein didn't think of the laser scanner in the supermarket. Yeah,
Yeah, that's true. That's true.
yeah.
That's true.
He had no idea of laser scanning. Yeah, and he
Yeah.
probably was beyond his imagination. Yeah, I guess. Yeah, but you know, it takes time. Yeah, and maybe
Yeah.
today we have already discovered some principles that we find fascinating. Yeah, but we don't
Yeah.
know exactly how to convert them into technology. Yeah, and
That's true.
and maybe, you know, you are much younger than me, and you're learning. I'm much younger than you. Yeah,
Yeah.
so one of them, yeah, will come up with the idea. Yeah, and you know,
Okay.
there are lots of problems out there that are looking for solutions. Yeah, and and maybe there are already solutions out there, but we haven't realized
Yeah.
what problem they solve. Yeah,
That's true. That's
there's
true.
also an issue. Yeah, maybe, you know, maybe we know something, but nobody made the connection that it can be used
Yeah.
to solve something else. Yeah, and
That's true.
and you know, you need young people with imagination and creativity, and anything is possible. Yeah.
Yeah. Okay. Thanks for that clarity. Um, so now, what are the subdivisions of theoretical physics, and then how many fields are there in this theoretical physics?
How many?
Fields of study of theoretical physics.
Okay, yeah. You know, traditionally, yeah. Um, if you when you start studying theoretical physics, there is a kind of
Yeah.
a traditional, sorry, build up. Yeah, you
Yeah.
start by studying mechanics. Yeah, you want to learn the rules of the mechanical world. Yeah, that's how levers operate and how apples fall, and
Yeah.
how pendula work, and how and those kind of things. Yeah, that's typically the first step. Then you move on to learn electromagnetic phenomena. Yeah,
Okay.
and essentially the theory of. So sorry, when you study mechanics, you essentially study Newton. Yeah,
Yeah. That's true.
the first step. Yeah, then you
Yeah.
study electrodynamics, which is essentially Maxwell equations. Yeah,
Yeah.
and then you can move on and start looking into quantum phenomena. Yeah.
Yeah.
You know, the moment you look at small objects, atoms, molecules, or even the constituents of atoms and molecules, nuclei, protons, electrons, neutrons, yeah, all of a sudden other laws apply. Yeah, and those are the laws of quantum mechanics. Yeah. And then you
Okay.
study the work of people like Schrödinger, Heisenberg, Einstein, yeah, yeah, and you learn the properties of this small world. Yeah. Then then you start maybe looking into another dimension. Yeah. You know, when in the example that I mentioned now, for instance, in mechanics, yeah, and you
Yeah.
think of the pendulum, yeah,
Pendulum.
you have just one mass point that moves, yeah, but the reality of many situations is different. That you have many mass points that move, yeah, and probably the typical example would be a gas, yeah. A gas
Yeah.
is made up of billions of atoms or small molecules
Yeah.
that swirl around
That's
and
true.
fill a volume or a room. You know, we breathe
Yeah.
air all the time. Yeah, that's a gas. Yeah, and you know, and the moment you put many particles or objects together, yeah, then you need to start thinking about statistical properties. Yeah, because you know, you can't describe them one by one. Yeah, you know, if you have
Yeah.
billions of particles or even more in filling a room, yeah, it's very difficult to describe them one by one. Even if you had access to the fastest computer of the world, it will be very challenging to solve the equations of motion for every single atom in that gas. Yeah? You can do it up to a certain extent, but at some stage you can't do it anymore. And then you need to start doing statistics. Yeah. Then you need to start looking at to learn how to look at statistical properties. Yeah? You have many particles, so you look at what do they do on average, yeah, so that so that you can introduce some kind of, we would call them the macroscopic parameters. There are some kind of simple quantities that describe a very complex system made up of many particles, yeah. And that's where things like temperature, pressure, yeah, and things like that come into play, yeah, which are kind of variables that describe in a simple way the properties of many particles, yeah, because you can't describe them one by one, yeah. So then you need to abstract to another level of description where you introduce variables that collect as kind of averages of the properties of the many particles, yeah. And that's where theoretical physics becomes statistical physics, yeah? And so that, you see, that's where you then start learning statistics, yeah. So that's why theoretical physicists also know about statistics, yeah, because there is a branch of theoretical physics called statistical physics, yeah. And you know, and the origin of the interest of physicists in statistics is because of this challenge of describing many particle systems, yeah. And then, but the same skills you can apply to many other things, yeah. So this is also another nice example of why training in theoretical physics is so important, yeah, because it trains you for many for many scenarios, yeah.
Okay.
You know, and then it goes on, and then there are more and more refined disciplines, and you can start studying relativity theory, quantum field theory, and so on and so forth, yeah. But roughly that's the you know, those are the dimensions that you need to study. You start studying the things that you know, we experience every day, yeah. The trajectory of a ball, the trajectory of an apple that falls. Then you start studying electric, magnetic phenomena. Then you start studying the small things, yeah, atom and molecules, and then you start studying the complex things, yeah. So there is the macroscopic, the microscopic, and the complex, yeah. Those are, you know, different dimensions that you need to be comfortable with as a physicist, yeah.
Okay, thanks for that, Prof. Now, tell our learners about quantum technology and what is quantum technology bringing to our world.
Yes, that's a very nice question.
Yeah.
You know, I mentioned before, yeah, that one of the dimensions that physicists and theoretical physicists learn is the microscopic, yeah, the laws that govern the atoms, molecules, and even the more elementary particles that made up our atoms and molecules, yeah, like the nuclei of the atom, the electrons, the protons, the neutrons, and so on and so forth, yeah. And
Yeah.
and that word is called it's called quantum physics, yeah. And quantum is a word that just describes a small quantity, yeah. And it's important,
Yeah.
because historically when people started looking into this thing, they noticed that certain phenomena happen in kind of steps, yeah. They don't happen in a continuous way. There are kind of little jumps, yeah. And those are the quanta, yeah. That's how the microscopic world operates. Yeah, you have systems that don't behave like continuously, like if a ball rolls down a slope, but jump up and down a kind of an energy ladder, yeah, from one state to the another, yeah. And that change completely the way we describe nature, yeah, because of course the quantum level is way more fundamental than the macroscopic level, yeah, because the desk that we touch, yeah, is made of atoms, and those atoms behave according to quantum physics. But when you put many together, it behaves like a macroscopic object, yeah. So those are the questions of quantum physics. And
Okay.
in quantum technology, you know, there are two levels of quantum technology. Yeah,
Okay.
the first level which some people call the first quantum revolution, yeah, uses let's say the more normal properties of quantum physics. Quantum phenomena are described by an equation that is called the Schrödinger equation, and Schrödinger was the guy who wrote it down for the first time 100 years ago. Yeah, so old guy, yeah, long dead. Yeah, and out of the experience of the Schrödinger equation, so, people came up, for instance, with the description of transistors that make the CPU of our computers, of lasers, and so on and so forth. Yeah, and that's by using, let's say, more standard properties of quantum mechanics. Yeah, and that was the first quantum revolution. Essentially, the revolution that gave us the transistor, the laser, and something like that. Yeah? But quantum mechanics has also more unorthodox properties. Yeah, that some people call spooky. Yeah, but I think spooky is not a nice word because it's
yes.
It scares people away because you think, oh, there are ghosts in quantum mechanics that do horrible things. Yeah. So maybe more than spooky, one should call them some different kind of resources. Yeah, that we don't have in the classical world. Yeah, and one of those things is for instance the fact that the quantum mechanics has something called the superposition principle, yeah, which is in the world of electrons, yeah, an electron with a certain probability, and here statistics come in again, in one position or in another one, yeah, and you don't know, where the electron is. It could be here, it could be there. Only when you measure it, you know where it is, yeah. So one spooky thing, yeah. Even more spooky thing is something called entanglement, yeah. And entanglement is, and you know, the word stresses that it's something that entangles, yeah, like a spaghetti. And that property is really amazing, yeah, because in quantum mechanics, this entanglement allows in a certain way correlations that are much stronger than what you would expect in the classical world. Yeah. So what happens, let's say, at one end of your room could influence what happens at the other end of your room. So they don't. Yeah. So that is a property of quantum mechanics. Yeah. That goes back also many years. Yeah. And then so and what we have learned over the last maybe 20 years or so is that this entanglement is not just something spooky that we don't really understand. Is in fact a resource. Yeah, it's something that you can really use to do things. Yeah, you can really use it to do things in a different way. Yeah. And then and the other element, yeah, and now sorry, I'm building up to the quantum technology. Yeah, why didn't we have quantum technology 50 years ago? Yeah, because 50 years ago, or even 20 years ago, or 30 years ago for that matter, yeah, we didn't know how to manipulate a single quantum particles. Yeah, you know, we knew about quantum properties, but always of kind of many particles at the same time. Yeah, we didn't know how to manipulate in a lab, yeah, a single atom. Yeah, we didn't know. We knew how to describe it, yeah, but we didn't have the technology to isolate a single atom or a single ion and start doing things with it. Yeah, move them, interact, put them apart, and ta-da. Yeah, we just didn't have the tools because it was just too small. Yeah. And so the two ingredients that led to the explosion of quantum technology in a positive sense, explosion, yeah, not in a negative thing. Yeah. We have now the ability to manipulate single quantum particles. Yeah. And at the same time, we know how to exploit these funny properties of quantum mechanics as a resource that allow you to do things completely different. Yeah. Allows you to do things. Yeah. That was the birth of quantum technology. Yeah. So those are the ingredients that you needed to really do quantum technology. Yeah. Already in the 80s. Yeah. So 40 years ago. Yeah. When neither you nor your students were born.
Yeah. Yeah.
Yeah. A gentleman called Richard Feynman. Yeah, he was a physicist in California. He also won the Nobel Prize at some stage. Yeah. He had the vision, and that you know, we know, and I told you before that fundamental level nature is quantum. Yeah, because we know that everything is made up of atoms. Yeah, so the fundamental level of description is quantum. Yeah, and he was thinking, if we want to build a machine that describes the quantum world, if we want to build a computer that is very good at describing what happens in the quantum world, then the computer itself should be quantum. Yeah. And you know, and that was in the 80s. And in the 80s, we didn't know how to manipulate single atoms. So yeah. So it was just a crazy idea. Yeah. But some people took it seriously and came up with theoretical concepts that in principle a quantum computer could be built. Yeah, and there was a gentleman in Oxford, David Deutsch, who came up with a proposal, yeah, of a theoretical quantum machine that can solve some problems. Yeah, and that was also just in the middle of the 80s or something like that. Yeah. And then there were two real breakthroughs. Yeah, one was by a gentleman called Peter Shaw. Yeah, and Peter Shaw came up with an algorithm. Yeah, so a mathematical procedure for a quantum computer that could solve a problem much faster than a classical computer could do. Yeah, and he could mathematically prove that if we had a quantum computer, that problem could be solved much faster on a quantum computer than on a classical computer. Yeah. The problem was the factorization of large numbers into their prime constituencies. Yeah? And it's very simple. You know, if I give you two numbers, yeah, let's say 5 and 7, and I ask you to multiply them, it's easy. Yeah, you just. But if I give you a number that has 1,000 digits, and I ask you, which numbers did I multiply? Yeah, it will take you a little while. Yeah, and
that's true.
The longer the number, the longer the time that you will need to factorize.
Yeah.
And what Peter Shaw demonstrated is that for a quantum computer, yeah, this task is very easy. Yeah. Yeah. Much easier than for a classical computer. Yeah. And you might think, or your listeners might think, why should I bother how to factorize a large number? Yeah, I just don't care. But you do care, because the factorization of large numbers is at the basis of the security that we employ on the internet. Yeah, you know, each of you probably does some kind of online banking. Yeah, and when online banking, or when you buy something online, you see on the screen in one of the corners there is the lock. Yeah, that indicates that connection is secure. Yeah, and the security of that connection is based on the fact that it is very difficult to factorize large numbers. Yeah. Yeah, and I mean, we don't have to go into the details, but that's the principle. So that is a kind of a mathematical complexity that we use to protect our communication. Yeah, and the discovery of Peter Shaw was a little bit of a wake-up call, because it meant that the moment we will have a big, powerful quantum computer, that kind of security won't work anymore. Yeah, because we will easily. Yeah? So that I mean, at the moment it's probably not really a major threat, but will become one. Yeah, it will become one, and it probably already is. Yeah, and but the situation is not desperate.
Yeah,
Yeah,
that's true.
because on the one side, quantum technology defeats the security that we are using now for communication with the help of this Shor algorithm. Yeah, but quantum technology gives us another procedure to secure our communication, and this is something that is called quantum cryptography. Yeah, and at the basic of all cryptographic systems, yeah, systems to protect the exchange of information, yeah, there is always the concept of a secret key, yeah. So if the two of us want to share a secret, yeah, we need to agree on a secret key, yeah, and the secret key could be something very, very simple, yeah. We could say A is 1, B is 2, C is 3.
Yeah,
Instead of writing ABC, you write 1, 2, 3. Yeah,
yeah, that's true.
not very secure. Yeah, because everybody who solves cryptographic games in the newspaper every day would crack it very quickly.
Yeah.
But
Okay.
we know now from other mathematical theories, yeah, that the best secret key that we could use to scramble our message, yeah, is a completely random sequence of zeros and one. Yeah.
Yeah.
If we are able to share a sequence of a random sequence of 0 and 1s, yeah, 0 1 0 0 1 1 1 0 0 1, yeah, something like that, but completely random, yeah, then we know we can 100% securely exchange information, yeah, because there is something called the one-time pad, but again, we won't go into the details. We can secure the information correctly, yeah, 100%, yeah, and quantum cryptography gives us exactly that, yeah, it gives us a protocol so that you and I can exchange 100% secure key, yeah, without anybody else knowing what the key is. Yeah, and once we have the key, we can and use it to encrypt a message and communicate our secrets. Yeah, yeah. So I can tell you the secret of what I will eat for lunch. Yeah, and nobody else but you and me will know. Yeah,
True.
yeah. So that on the one side, quantum computing, yeah, is a challenge to how we protect information at the moment, yeah. And on the other side, quantum cryptography shows us how we can protect it, even if we have computers, yeah.
Okay.
And those were a little bit the two breakthroughs that made quantum technology really relevant, yeah. And and the vision, yeah, of quantum technology, yeah, is essentially to replace our internet with a quantum internet, yeah, with an internet that operates according to the rules of quantum mechanics, yeah. So that an internet in which you will connect quantum computers that will communicate with each other with quantum cryptography and other fancy quantum gadgets. Yeah. So this is what quantum technology is about. So the buzz about quantum computing is that, in the meantime, we know that there is not only the algorithm that Shor invented that from quantum computers. Yeah, there is even a website called the Quantum Algorithm Zoo, yeah, where you can go and you will see there are hundreds and hundreds of algorithms to work on quantum computers to solve all possible sorts of things. Yeah. At the moment, and we are also working on that in Durban, there is a lot of interest in using quantum computers for machine learning tasks. Yeah, machine learning is now everywhere. Yeah, it's the of the fourth industrial revolution, or one of the buzzwords of the fourth industrial revolution. And because now we have small quantum computers available to us in the cloud. Also a new thing. Yeah, now you in the cloud, yeah, and not on your desktop. Yeah? People start thinking, will we be able to do machine learning on quantum computers? Yeah, and there is some strong evidence that it will work. Yeah, and we know that it works already to solve small problems because we don't have yet big quantum computers. Yeah, but that, you know, we discussed at the beginning the role of theoretical and experimental physics. Yeah, you know, the theoretical physicists came up essentially with the idea of a quantum computer and what it could do, how you could build it in principle, yeah, how the algorithms will work, yeah, how the error correction will work, yeah. But now we have the engineering problem, yeah, of building it, yeah. You know, okay. We understand the physics, yeah? We know the equations, yeah, we know how to model it, yeah. But there is the engineering challenge of scaling up the small quantum computer that we have already built, so that we can attack the really big and good problems that the world is throwing at us. Yeah, you know, from climate change to COVID. Yeah, those are all problems that need large amounts of computational power and analysis of very large data set. Yeah, that's why people speak.
Yeah. Okay.
That are so big that they won't fit in your laptop.
Yeah. Okay, Prof. Now let's go to another question. You know, you did talk about fourth industrial revolution. So, can you please tell our learners what is fourth industrial revolution, and then what is it that is doing, that is changing the world?
Yes, you know, my guess is probably as good as yours. Yeah, but what people mean in the, you know, we've been through a few revolutions, a few industrial revolutions. Yeah, first industrial revolution was around the invention of the steam engines. Yeah, and for the first time, people had machines that could replace what previously you had to do yourself. Yeah. You had, for instance, some oxes pulling big weights from here to there, yeah. Pulling heavy carriages from here to there, yeah, or some horses or something like that. Yeah, so that was really a qualitative jump, yeah, in productivity, yeah, because now you had a machine. You put in coal burns, fires, steam, and with the steam you could move apparatuses, yeah, and you could have textile factories and things like that. You could replace manual work with machine work, yeah, and increased a lot of productivity, yeah. And you know, let's use this example to address another question that your listeners might be interested with. Yeah, because usually when there are these technological revolutions, the technological advances, yeah, like the steam engine, yeah, people think, oh, but now all the people that were working in the factory by hand will be replaced by a machine, yeah, and you know, and that is of course true, but it's not necessarily bad, yeah, because those people will be able now to do better jobs, yeah, they will be able, you know, instead of lifting heavy things from here to there, yeah, that the machine now does for them, yeah, those people will be able to operate the machine, yeah. So the technological revolutions come very often, yeah, also with an increase in the quality of life of people in the long term, yeah, because you know you might lose a category of jobs, but you create many other categories of jobs, yeah, that are much probably better, yeah. And so the steam was the first industrial revolution. Afterwards came the electric revolution. Yeah, we had electricities in our homes. Yeah, we had light in our home, and that, I mean, and with electricity, we could replace steam engines with electric motors, for instance. Yeah, that was also another huge thing. Yeah, first of all, because electric motors can be even small, so they can do small things that the steam engine might not be so good at. Yeah, and you know, and the advantage of having electricity are really huge. Yeah, you know, you can learn in the dark, you can heat your food, you can many things. Yeah, you can operate, you can, you know, now we have even electric cars. Yeah, so it was really a big thing. Yeah. Okay. The third industrial revolution that gave us essentially the laptops that we are using now. Yeah, that gave us the computers. Yeah, and you know, and with the computers came another level of automation, because you can have little computers in your car, you can have little computers in your pocket. Yeah? Your washing machine has a little computer inside to if you change the program. Yeah? So that was really another level. Yeah, and now you know, and now the computers have become so powerful. Yeah? That they can really do things that we cannot think of doing manually anymore. Yeah, and that's where the fourth industrial revolution kicks in. Yeah, which is concerned about essentially bringing together, yeah, the cyber world, yeah, and the physical world. Yeah, so you know, I don't know if you have, for instance, a smartwatch, yeah, that measures the steps that you walk every day. Yeah, for instance. You know, that's an example of bringing together the cyber world and the physical world. Yeah, because you know, you start your day and you say, I need to do 10,000 steps. Yeah. True. And it's a watch that tells you how many steps you've walked, and then you can decide, I've done 6,000. I need to go for another walk. Yeah. Yes. The cyber world starts to influence your physical world. Yeah, because you watch what the watch tells you. Yeah, you react. Yeah, you know, another example is, for instance, the GPS. Yeah, you have your GPS on your in your phone. You look at Google Maps. So I don't know if you're allowed to do advertising. Or whatever other map you use. Yeah, and that affects how you behave, because if you want to go and visit a shop in a part of town that you're not familiar with, yeah, you just type it in your GPS, and it leads you there. Yeah, true. That's another example of the confluence of the cyber world and the physical world. Yeah, but now the computers are much more powerful. Yeah, and that's where big data and artificial intelligence kick in. Yeah, because now we have the ability to analyze huge data sets. Yeah, in a very efficient way, and learn from them. Yeah, so you know, for instance, a typical example now with COVID. Yeah, and this for instance, the contact tracing for COVID. You know, we the South African government is promoting that we use an app that informs us that we came next to someone who has COVID. Yeah, and careful, you were in contact for 15 minutes with someone who has COVID. You should stay at home in quarantine. Yeah, so that you don't to other people. Yeah, and that's typical fourth industrial revolution. Yeah, because that means that there is, in the background, there are lots of data that are being collected. Yeah, in an anonymous way, because to protect the private information of people, of course. But there are lots of data connected. Yeah, and a lot of computational power and artificial intelligence goes into then detecting the cases when you hopefully never, but might have come close to someone with COVID that could have infected you, so that you are warned. Yeah,
Okay.
and you know, and that you couldn't have done 20 years ago. We wouldn't have
Okay.
the
Thanks.
yeah? And
Thanks.
these
Thanks for that.
are just examples. Yeah, there are many, many. Yeah.
Okay. Prof, thanks for that. Tell our learners what South African scientists did in 2010 World Soccer Cup.
Yeah, no, we did it. Yeah, you know,
Yeah.
I told you, no, that's something. You know, I told you about this quantum cryptography. Yeah.
Yes.
Which is the most secure way to protect information. Yeah, and in fact, it's unbreakable. Yeah, because of as I told you before, it's security that is based on physics and not on mathematics. Yeah, if security is based just on mathematical complexity, by using bigger and bigger computers, eventually you can crack it. Yeah, but if the security is based on physical laws, yeah, that govern nature, yeah, there's nothing you can do. These are the laws of nature, yeah, unless the laws of nature break down, yeah, which I don't think so. But unless that happens, you are safe, yeah. And in 2010, when there was the soccer World Cup, the FIFA World Cup, and in Durban, there was one of the stadia that was used for the soccer World Cup. We had a collaboration with the Etequini municipality, which allowed us to use the fiber optical cable that was connecting the risk management center in the stadium with some risk management center outside the stadium and we protected the information on that link with quantum cryptography. Yeah, and and it worked. Yeah, you know, I had a few sleepless nights because I thought if it doesn't work, they will come to us. Yeah, but it and that was really very nice, because it was the first time I think that quantum cryptography was used in an event that that was of global interest, because you know, everybody watched the soccer cup.
Yeah, that's true.
Yeah, so that
Okay.
an application of quantum cryptography and a demonstration that it works in practical, real, everyday's life. Yeah, because there was lots of video streams and phone calls and lots of things going in that optical fiber. Yeah? So it was used 24/7 for the whole months of the World Cup. Yeah.
Okay. Interesting. Okay. Now, since we are in a COVID-19 pandemic, what is it that theoretical physicist or theoretical physics is trying to do to solve the problem?
Yes, many things. Yeah, you know, let me again use personal experience. Yeah, you know, some theoretical physicists, and one of them is also South African, Professor Neil Turok. Yeah, and a colleague, Professor Wilfred Ndifon. Yeah, they came up with a mathematical method. Yeah, to for pooled testing. Yeah, so a mathematical method that allows you to test, let's say, 100 people. Yeah, in which much fewer tests. So instead of testing them one by one, you pool the tests together, and there is an algorithm that allows you. And for instance, what we can do at the moment is if you have 81 people, you just need 13 tests to find the person with COVID. Yeah, so that is an enormous savings in terms of money and time. Yeah, and Professor Neil Turok and his colleague Wilfried Ndifon, they came up with a model. Yeah, and we read their paper. Yeah, and we understood the mathematics. So we approached our colleagues in the medical school. Yeah, and they started to do the experiment. They started to test whether this mathematical method works in practice as well. Yeah, and now we know. Yeah, and in fact, we just started writing a paper together. Yeah, theoretical physicists and medical people. Yeah.
Yeah.
So this is also a thing that is new for the fourth industrial revolution. Yeah, that as a theoretical physicist, you can start working with medical people to solve problems that are really interesting for everybody. Yeah. So now in the lab of the medical school at UKZN, we have the capability of detecting one case of COVID out of a pool of 81 people, yeah, with a dozen tests. Yeah, so you save almost a factor of 10. Yeah, and of course, if in that pool of 81 nobody has COVID, you just need one test. Yeah, which is almost a saving of a factor of 100. Yeah, and now we, before suggesting that everybody has to use it, we wanted to test it properly. Yeah, and but now we are writing up the paper, and we hope that soon we will submit it and will publish, and hopefully then many people will start using it. Many other labs will start using the same method because it just works. Yeah, and it lead to lots of savings in terms of time and money. Yeah.
Okay.
Just an example. Yeah.
Okay. Thanks a lot, Prof, for that. Now the next question is very personal.
Okay.
It's directed to you, obviously. Okay. So now, what? Tell our learners what inspired you to pursue theoretical physics. Who was your motivations? Tell us your side of story. Yes.
I started getting interested in physics in high school. Yeah, and
Okay.
I had a very good friend who sort of introduced me and hooked me with physics. Yeah, he was in my class. Yeah, but he developed his passion a little bit earlier. Yeah, and he started building when we were in high school at home a cloud chamber. Yeah, which is a little setup that allows you to see the elementary particles that swirl around that comes from that hit the earth from outside. Yeah, it's something that 50 years ago it was big science. Yeah, now in principle you can build it on your own at home.
Yeah.
With a glass box like a little fish aquarium. You can modify it so that it works. Yeah, and that I really found fascinating. Yeah, because that really hooked me. Yeah, the idea that you could build on your own a gadget that allows you to see electrons and other things on your kitchen desk, yeah, on your kitchen table, yeah. That was really fascinating, yeah. And but then somehow I was not so good at building stuff, so I developed more an interest in the theory, yeah. But that's how it started, yeah. And then after high school, I started studying physics, and I'm still working in physics, yeah.
Okay. Okay, interesting. The last question, what is your last message to those learners who are interested in studying theoretical physics as a career? Your words of motivations.
Yeah, no, the motivation is very simple. I mentioned that it's not an easy thing to do because it's a trajectory of studies that in particular at the beginning can be quite challenging. Yeah, but it's very rewarding. Yeah, because you learn lots of skills that you can apply in the most diverse areas of science and business and industry. Yeah, and one of the skills that you learn as a physicist and as a theoretical physicist, and that I tell also all my students, yeah, is you learn programming skills. Yeah, because physicists are not afraid of using computers. Yeah, so they use them. Yeah, so you know how to program computers, you know how to design software and things like that, and that is your life insurance. because these days if you have programming skills, you will always find a job. Yeah, worst case scenario, you just develop websites for someone. Yeah, having programming skills is a kind of life insurance. Yeah, you know, you are able to program robots. You can design websites. You can set up a network for some people that don't know how to plug together different computers, a router, and things like that. Yeah, that's kind of your life your life insurance for the fourth industrial revolution. Yeah, because not everybody has those skills. Yeah, and and of course you have even more skills. Yeah, so that makes you even more precious to the work market. Yeah. But you know the fascinating things of theoretical physics is just the process of understanding things. Yeah, you know, once you went through the experience of understanding something that maybe nobody before you understood, then you are hooked. Yeah, and you know, and that experience you can apply everywhere. Yeah, you can apply everywhere. Yeah, you can maybe work in a logistic company and help them optimize their logistics. Yeah, that's a kind of problems that physicists working in complex systems also address all the time. How to optimize things, how to find shorter paths from here to there. Yeah, that's something that physicists learn. They don't learn in their curriculum how to apply it to the logistics of a big company. Yeah, but the methods are the same. Yeah, so it's something you can learn quickly. Yeah.
Okay. Thanks everyone for watching. I also want to thank Prof for his time. He's a busy man, but today he decided to be with us. Thanks, Prof, to you also, you know, for leaving us today.
Aluwani, it is a big pleasure, and we can do it again anytime. Yeah.
Okay, thanks a lot.
Thank you, Aluwani. Have
Bye.
a good bye. Bye bye to
You too.
yeah. Bye. Bye bye.